this is beginning of a video series. Probably go over every single question if possible in the textbook Linear Algebra by Axler. The objective is sort of just to go through every single question, but they probably won't get to there. So we'll start from section 3b. This is already fairly late in the semester. So question 1, an example of linear map such that dimension no space is 3 and the range is 2. This one's not that difficult, I think. So what you want to do is map. So say you have 5 elements, what you want to do is map them to something like this. Of course, the sheer volume of questions means that most of this will be an intuitive recording or overview of the key concepts here. Okay. So most of this I've thought about while walking somewhere or just doing nothing else interesting. So this is just to record down my thoughts and be able to review it at some point. Suppose V is a vector space and there's 2 linear maps inside the set of linear maps from vector space V to itself, such that the range of S is inside the null space of T. And then consider showing that square root of ST composed is 0. So I think intuitively this makes sense, because if you have ST composed, that just means the composition of ST performed on another composition of ST. And if you take some arbitrary member of the set, then what will happen is when it gets through the first set of ST, it will be in the range of this S, which is in the null space of T. So this will then get mapped to 0 and S of 0. So the linear map of any element 0 is also 0, as evidenced by a quick proof like this. Perhaps if you go here, then I think that's somewhere in the text. So yeah, that's pretty interesting, but not that bad. So then consider a list of vectors in V, define it by some sort of, so you're mapping from, let's say, Fm into V. Okay, it's not entirely clear how to think about this just yet, so I'll just write some things down. So first thing that comes into mind is that, in fact, V and Fm share the same dimension. So what probably should happen is you should map the bases of V to, or the bases of Fm to the bases of V, in which case then it would work like that. And here's asking about what property of T corresponds to this spanning V. So first that, oh wait, no, it doesn't even say that. It just says, I thought V once review on was a basis in V, that stuff. Okay, so we don't know the dimension of V, so there's no, you can't approach it that way. Right, yeah. What property of T? So you're probably looking at the range. If the range of the dimension, the range of T is the same as the dimension of V, then you're good. But I'm not sure if that's a property of T. about the linear independence, what you probably want is you want the dimension of the kernel to be 0. Because otherwise, if you got kernel is not equal to 0, then there exists two separate sets of z's, so that we call them like z's1, z's2, so that if you give them a t transformation, then they map to the same thing, which is not good. Because then what happens is that you got two non-trivial linear combinations of whatever, two sets of this kind of thing, where they're equal to each other, and then they're not linearly independent. Yeah, but the tricky part might be thinking about how like the coefficients of this is non-trivial and the coefficients of the v's on the left hand side is not equal to the coefficients on the right hand side. So you get, when you do this subtraction, you get at least one non-zero coefficient there. So to claim there's a non-trivial linear combination, which results in the vectors not being linearly independent. Right, so let's take a look at this. Dimension null space of T is greater than 2. It's not a subspace. Okay. So anytime you want to show something is not a subspace, of course you want to target it at the properties of the subspace, which are zeros in the subspace. So if you try to target it here, then it probably doesn't work, because in fact mapping everything to 0, for example, mapping all of R5 to 0 is in fact having a null space greater than dimension greater than 2, because the dimension of null space is 5. And then the second place you want to target it is the second requirement, I think, which goes something like this. So let's see if I can remember it. Oh, right, it's the additive closure. Yeah, blanked out for a moment there. So what you want is the additive closure. So you have a member of the linear map such that null space is greater than 2, and you combine it with another linear map, something like that, then you get a third linear map, which also has a null space larger than dimension 2. So in fact, that's probably wrong, and the reason is because what you could do is you could have a first linear map, let's say map E1, E2, E3, and these ones all map to E1, E2, E3 of R4 from R5. What you could do is you can have E4 and E5 both map to 0. And this way you get no space of 2. You do something very similar with another linear map, but this time you make E1, E2 map to 0, while E3, E4, E5 map to E1, E2, E3. This way, when you add them, then this gets E4, E5 now maps to E2 and E3 because of this nice 0 that you map to. So I think that it's possible to say that this breaks the subspace requirement. And the scalar requirement usually doesn't really work that well. I think is that if you multiply by a scalar, then if you have a linear map L and multiply a scalar C, then CL is still in the subspace. That doesn't really work well with something like this, because I think if linear map of E4 or any multiple of E4 or E5 goes to 0, and then if you multiply them, it still goes to 0, so it stays fairly consistent with something like that. Alright, let's go example 5. I'll give an example of a linear map such that the range is equal to the null space. Yeah, there's an interesting example. So you want to maybe map E1 and E2 and R4 into 0, and then E3 and E4 into E1 and E2. This way the null space and the range are equal, so that's not too bad. So prove there does not exist linear map to map from R5 to R5 such that range is equal to null space. So first, for them to be equal, like they have to have the same dimension, which in this case, by the fundamental theorem of linear maps, what you could deduce is the sum of their dimension will add up to 5. But also maintaining the fact that they're equal. This is impossible because 5 is an odd number, so you can't break it up into two of the same number. So you get 2 plus 3 or something like that. So in fact, it's impossible. Okay, so suppose V and W are finite dimensional with 2 is less than equal dimension of V less than equal to dimension of W. Show that T, which is a member of the set of linear maps from B to W, where T is not injective, is not a subspace. Yeah, I thought about this briefly, and it didn't work out, so I thought about it longer. So this is what I realized. So there's something interesting going on with this set of inequalities, 2 less than dimension of V, less than dimension of W. What you want to realize is they set it up this way is if dimension of V, so talking about this less than equal sign, if the dimension of V is less than the dimension of W, then the set of linear maps from V to W has, there's only one possibility, is that it's not injective, because you're mapping to a lower dimension, so you must have two bases mapped to the same, 2 elements of your bases in V mapped to the same element in W somehow. But you can also show this in a more rigorous way with something like the fundamental theorem of linear maps, where you have the dimension of the kernel of V plus dimension of the range being equal to dimension of V itself. And since we notice that dimension of range is not greater than W and W is less than V, then kernel has dimension greater than 0, and that implies it's not injective. That implies that it's injective. So to make sure that the entire space isn't just filled with injective functions, they impose this requirement. And a similar situation is this: if you only have one dimension, then there's not really much injectivity you need to worry about. So I was thinking about that. And now you want to give maybe an example of how this is not a subspace. So you want to, like in a previous example, contribute something that breaks the subspace requirement. In this case, I think the additive closure works very well once again. So what you could do is you could imagine E1, E2 is the basis of V somehow. And then W probably something similar, right? What you want to do is probably map E1, E2 of V into 0. You want to map E1 to 0 and then E2 to E1. And in another map, probably you want to do is, so I'll call this L1 and L2, you want to map E1 of V to E1 and E2 to 0. Or, no, sorry, I probably should do this. And then when you add them together, then E1 gets mapped to E2 and E2 gets mapped to E1, which is not injective. So I think that works fine. It's very similar to question 4 or 5, something like that. So now you have V and W are finite dimensional with the dimension of V greater than equal to dimension of W greater than equal to 2. I want to show that the set of surjective maps is not a subspace from T to W, that is. I think once again here there's some interesting things going on with the inequality dimension of V greater than dimension dimension of v greater than or equal to dimension of w is greater than or equal to 2. So the dimension of v is forced to be greater than or equal to dimension of w, because if dimension of v were less than dimension of w, then what could happen is that every map is not surjective, right? So then all the not surjective maps again form the entirety of the set of linear maps, which then it would be a subspace, because everything in that set there's no way you can get out of that closure. But if you have a situation where you have not surjective maps and surjective maps, then you can get out of that closure of not surjective maps and somehow enter into the set of surjective maps while adding two non-surjective maps. So we're trying to give maybe such an example. So consider such a case where you have a linear map L1 and a linear map L2, and once again we establish the basis of V as E1, E2, and the basis of W similarly E1, E2. So E1 once again maps to 0, E2 maps to E1 in linear map 1, and in linear map 2, E1 maps to E2 and E2 maps to 0. And adding them up, I think once again you get L1 plus L2 now maps E1 to E2 and E2 to E1. And that once again is now a surjective map. Something interesting, or something like a trick about most of these questions, is you want to map things to 0. And this way, whatever you map in the second map basically becomes what is mapped to in the entire sum of those two maps, which is a nice trick. So question 9, suppose that the linear transformation like this is injective. And we once reviewed our linearly independent proof TB1 or TB1 is linearly independent. So this is actually not too bad, because first you want to realize that anything in the range of t, which is what TB1 through TB and Rn, there must exist. So first, before perhaps we even do all that, suppose a linear combination exists such that these things add up to 0, right? And the non-trivial linear combination exists. And then what you can say is that you can rearrange the linear combination in such a way so that the unique non-zero coefficient, or it doesn't have to be unique, but in the worst case it probably is, gets mapped to something like this. I don't know. And then what you could say is that without all those t's, if you just look at the linear transformation, its input then these two are equal to each other, which shouldn't happen, right? Because if these two are equal to each other, that means we want to be and aren't really linearly independent. So then it's quite a bad situation. So you arrive at a contradiction. Of course, like these two inputs must be equal because T is a injective map. So if transformation of this is equal to transformation of that, then this and that must be equal. So that's question 9. Question 10. So you suppose that V1 through Vn span. You suppose they span V, and linear transformation is in the set of all linear transformations from V to W. And prove the list spans range T. So I think this is not so bad. And the reason goes something like this, right? So suppose you choose some arbitrary element in range T, like I don't know, choose arbitrary element t in range t, and then t must be composed of some sort of input, or sorry, t must be the linear transformation t acting upon some sort of element v and v. The reason is because t is in range, the range of the linear transformation, so there must exist some input to make that output. And then that input is broken down into a linear transformation of, a linear combination of the spanning set of v. But if you stare at it for a bit longer, then you see this, right? Which means that really that you can break t of v down into a linear combination of the transformation of various v1, v2, etc. through vn. That it is indeed spanned by those vectors, because any arbitrary v can be described as a linear combination of tv1 through tvn. Okay, I think that'll be it for now, and I might come back later for a second round once I figure out what the rest of the questions in 3b are.